Okay, so this is week 2 in the statistics class. What is this, Psych 250 for you folks? It's really weird that you have stat after experimental. That's really bizarre. But, you know, that's the way that things are done around here. A lot of colleges, they do it the other way. You take stat and then you learn about studies. But this is the Mary Baldwin way, so that's the way we do it here. So, for this particular unit, what we're going to start with, if you look at the agenda here, last week you did a few computations, some kind of things. We'll review that actually towards the end of class. But let's take the following situation here. I'm teaching statistics. Wow, there's a new situation at Mary Baldwin and JMU. You guys know anybody taking classes at JMU? Okay, but you could. Taking classes at Mary Baldwin and JMU during the summer to psychology students, and it turns out that in each class there are only 3 people in these classes. I ask all of the students if they like statistics. I use a 5-point scale with 5 being very positive and a 1 being very negative. So I have the following data set for the group at Mary Baldwin College. The numbers are 2, 3, and 4. And for the group at JMU, the numbers are 1, 3, and 5. Now notice I put the word population here. Does anybody know why I use the word population versus sample here?
Because there's only 3 people in the group, so that's automatically the population. So the sample, right?
The voice from beyond. So indeed you are correct, Ashton, that because I only said that there are only 3 people in the whole class, these 3 people represent the population. That's going to become a little bit important later on. These 3 people represent the population. When in statistics we're dealing with populations, we use Greek symbols to represent population. Somewhere in your book it probably says that. Casey, can you back me up on that? I see you looking at the book there.
No, I was writing down central.
Oh, okay. So the idea is when you're dealing with a population, actually maybe I should break out my books. I lugged them here. Both versions. When I took statistics and I learned with this book, guess what version it was?
2.
It was versions 1 and 2. Actually, it was 2.
It was in
I didn't take 2 years to learn it.
It was in the YouTube thing that I rewound in front of 58 times.
There you go. So, let's see. So it is in fact a population that we're dealing with here because we only have 3 people in it. Use Greek symbols to represent population. So if you look at these 2 data sets, and I like to work with simple data sets here, how would you say are these numbers same? Or does it look like these people did about the same? Or their attitudes, were they about the same or were they different?
They're very similar.
The averages are very, very much the same. So if you were to look at measures of what we call central tendency, the measures of central tendency here are pretty much the same. What's the main measure that we often use in psychology to measure central tendency? Mode is one of the terms. There's the mode, there's the median, and there's the mean. The one we most often use in statistics is which? The mean. We most often use the mean. The mean is usually considered the best measure of central tendency. And central tendency, once again, is the idea of where do the data cluster. Central tendency says we have to have one number that really shows where the numbers are clustering. That's our measure of central tendency. So in this case, the mean is the one that we most often use. The mean is, how would you get the mean for each one of these? What's the formula for getting the mean?
Like calculating the average.
Calculating the average. So we would add up each score and then do what? Divide by 3. And by the way, if this seems so simple and stupid that anybody could do it, that's just how I teach statistics. A lot of people have fear of numbers and statistics. Most of my examples are going to be relatively simple to teach you and then maybe a little more applied down the road here. So the idea of 2, 3, and 4, the mean is 3 for both of these. What symbol would you use to represent this? You know what symbol you use to represent the mean? It might be in the book here. Since we bought the book, some of us on my wrong advice. I think we're in chapter 3 here. What symbol do we use to represent the mean? It's actually, if you look in the newer book in version 9, it's mu. It's a U symbol. It's on page 75, the population mean. And I think you've got something. Ashton, do you have the book before you as well?
Yes, and I have found the usable.
Yeah, so the written word for it is mu. Mu is the like U symbol, but it's a Greek letter because Greek means it stands for what? It's coming from a,
Population, not a sample.
there you go, it's coming from the population. So we could get the mean of both of these. You add up the scores, the sum of x over n, right? Is everybody comfortable with this? Pretty simple stuff. So in this particular situation, if you were to look for the measure of central tendency, you would say both of these are pretty much similar. But would you say they're identical, these data sets?
No.
No. So let me see here in the classroom here, how are they actually different? If they're not different in terms of their central tendency,
The lowest average is a 1 for one, and a 2 for the other, and the highest is a 5 for one.
so it looks like the data set from JMU has more what we might call variability. Say again?
Variability.
Variability or dispersion. There might be more dispersion or variability among data set number 2. The scores are more spread out for that data set. When you look at any data set, many times what statisticians want to know is where's their central tendency, and then they also want to know what is their dispersion. Do you think statisticians prefer when there is more dispersion or less? Less. Dispersion is a measure of error many times. So the less dispersion you have, the better. When you eyeball this data, which one does it look like does have less dispersion? Say again?
The first set.
Yeah, the Mary Baldwin College data set 1 looks like it has less dispersion. The most simple measure of dispersion that we have is the range. Some of you may feel at home on the range. I would have made that bad joke acoustically, wouldn't I have? My father often said that, Stuart, people aren't laughing with you on your jokes, they're laughing at you when you make these jokes. And I said, that's fine because it keeps people awake when they're learning statistics, because this is a pretty boring subject. So the range, what would be the range for data set 1?
2 to 4?
Yeah, it's 2 to 4, so the range is 2. For data set number 2, the range is
Oh, 4.
4. So you could mathematically say that there's more dispersion on the basis of the range for data set 2 because there's more dispersion there, or 1 to 5. There is actually more precise measures for measuring the range, but they get into all sorts of fancy math that there's no good reason to do that. So we're not going to do that. You can get just complicated in a hurry for no reason. There's going to be plenty you can get complicated on for no reason in this class, and I generally don't do that unless there's a good reason for having you do that. So the range, one measure of dispersion is the range. Now you might think, well, that'd be a nice and easy thing to use, but it turns out we don't often use the range. It's just too darn simple for statisticians to use. We like to have things that are more complicated than that, for better or for worse. So the range is one measure of dispersion. The next measure that I'd like to talk about here is a measure of dispersion, and it's on the outline here. I tried to lay it out for you pretty good. What does it say there? The sum of the deviations from the mean. So notice what I wrote in the symbols there. The sum of the deviations from the mean. So x represents what on my outline?
The number of data.
It's actually each individual score. So x here, if it's data set 1, would be the number 2, the number 3, and the number 4. What is mu?
Me.
The mean, which is going to be 3. And it doesn't say here, because I couldn't draw it in, but the summation sign. Are you all familiar with the summation sign?
I'm not.
It's the big E thing.
Oh, okay, yeah.
Let's see if this is actually shown. Maybe in chapter 4. Chapter 3 was fun, wasn't it? Yes, if you look in chapter 4, It's towards the beginning of chapter 4.
What is that?
Yeah, it kind of has the deviation score. So what I've asked you to do is the sum of the deviations here. The idea is, see if you can do this for the first data set here. The sum of the deviations and the mean. What would we do? So what would be the math of that? I want you to get the sum of the deviations and the mean. So what would be the math for that?
Each number minus the mean, and then sum those.
So add that up. So it would start off with 2 minus what? 2 minus 3 plus 3 minus 3 plus 4 minus 3. If you add all of that up, what are the sum of the deviations from the mean?
0.
0. So that doesn't seem too useful. Why don't you do that with data set 2 as well?
Yeah, same thing.
Same thing. You've just proven something here. You have proven that the sum of the deviations from the mean always add up to what?
0.
0. So you may want to write this down. We have just proven that the sum of the deviations from the mean always equals 0. That might be important a little bit later. And you might be scratching your head right now. Because we wanted to find something that might be useful for dispersion. Is this ever going to be useful for dispersion?
Nope.
No, because it's always going to be what? 0. How could we fix this problem and have this be a useful measure of dispersion? You're giving me that look like this is too dumb to possibly do here. No, it's good.
The next thing, square.
There you go. The next thing. So let's take the same idea, and instead of doing the sum of the deviations, it's fine. Instead of doing the sum of the deviations and the mean, let's get the difference, the deviations and the mean, but let's square each value now. Let's square each value now. So now, instead of having for data set 1, 2, 3, and 4 and getting the mean and getting the deviations at 0, can you guys tell me what that computation would be? Time to put on the Jeopardy music.
Would you do 2 minus 3 squared and plus 3 minus 3 squared?
Plus one more.
Plus
Plus.
4 minus 3 squared?
So what do you get when you sum the square deviations from the mean? What is that final value? You all did it.
2.
2. Did everybody get 2? No? Did you get? So what you have to do in your math is, if you look up on the board, did you get 2, Ashton?
Yes.
So what you have to do is 2 minus 3, quantity squared. Let's see. I don't have to write in the experimental class, but the idea is 2 minus 3, quantity squared, plus 3 minus 3, quantity squared, plus 4 minus 3, quantity squared. I'm a member of the Piss Poor Penmanship Hand Club, as you can probably tell.
Okay, I think maybe I misunderstood the question. I did get 2 for the Mary Baldwin group.
That's right.
Okay.
So this number that you just got, this is really the first important number in the variability of statistics. You just computed something called the sum of the square deviations from the mean. You got the sum of the square deviations from the mean. But that's such a long term, we often call that the sum of squares. That is called the sum of squares, or the SS. This is called the sum of the squares. The sum of the squares for data set 1 was 2. What is the sum of the squares for data set 2?
8.
8.
See, I was coming up with 10 because I
There you
wasn't
go.
listening.
The sum of the squares for data set 2 is 8. Is this correct? How did you get 8?
The negative 2 squared is 4 and the 2 squared is 4 and the 0 is 0.
So you went 1 minus 3 squared, plus 3 minus 3 squared, plus 5 minus 3 squared, and you add them all up and you get a total of 8. So this,
You call that the SS?
that's called the sums of squares. It's really the sum of the square deviations in the mean, but I've already been talking for 2.5 hours and I need to shorten my lingo, so I'll just say the sums of squares. The sums of squares for data set 2 is 8. Is this useful? Yes.
It looks a lot more useful than the other one.
It looks a lot more useful because the measure of dispersion, should it actually have a higher number for data set 2?
Yes.
Yes, data set 2 had more variability in it when we just eyeballed it, so the fact that that number is an 8 and the other number is a 2 makes good sense. One rule of thumb, and actually, Ashton, did you have a question?
Mm-mm.
One rule of thumb, actually, let me give you one other data set to figure out. What if I gave you the numbers 99, 100, and 101? Let's say you had 99, 100, and 101 Dalmatians. And I asked you, what is the sums of squares for that? Nobody even giggled at 101 Dalmatians? Did you guys see that one? No?
Is that a,
Disney,
is
please.
it considered two? Is it considered 2 or 3? Do you count 99 and 101 to come up with?
So the question is, what is the sums of squares of 99, 100, and 101? The correct answer is? So you're not sure if it's 2 or 3. What did the rest of you get? 2. Is it working or no?
No, would it be the same if it's 2, 3, and 4? Are they the same in all the columns?
Because you're measuring the variability. What if I gave you 1,000, 1,001, and 1,002? The spread of the scores. So what you have learned is that any 3 consecutive numbers, the sums of squares are always what? 2. That may be a good rule to write down. Ashton, is that working for you?
You said any three, when it comes to any 3 consecutive numbers, the sum of squares will be 2?
That's correct. That may be important down the road. And actually, the other data set, the 1, 3, and 5, if you're spread out by 2, it's always going to be 8 for that, but So any 3 consecutive numbers, the sums of squares are always going to be 2, because what is this measuring?
The validity?
Not quite the validity,
The variance?
the dispersion, yeah, kind of the variability of the data set. So any 3 consecutive numbers, the sums of squares are always going to be 2.
How did the math on that work out? It's like 99 minus 3?
No, it's not 90. So if it's 99, 100, and 101, what's the mean of that?
100?
Do the mean of that, okay.
Yes, the mean is 100, so you have to take it minus the mean of whatever that group
I was
is.
doing the-
It's good.
for the-
But it's a fine question to ask, because out of every 10 people, I might get something like that. So you have to do it minus the mean of that group.
Okay.
Mhm. And how did we get rid of that problem with the 0? We square it. What if I gave you a sums of squares and it was negative 10? What could you tell me? If I told you the sums of squares was negative 10, what could you tell me?
Should be squared.
You could tell me that I screwed it up. Sums of squares can never be?
It
Negative.
can't be negative because you squared it.
Yeah, sums of squares can never be negative. People can. It's going nowhere. Think about what my dad said. Okay, boy, this tape is going on and on. I feel sorry for these people. Okay. What else are we going to do here? Time to stop the tape. Wow. I can't even see it. 19 minutes of this?